So these are the official units of the 7 base properties that matter can have. So there are other properties that matters can have, volume, density, and those are all combinations of these base units. The first type of unit we're going to work with that is a combination of units is the density of a substance. I mentioned before it is the mass per volume of a substance. This is what makes it an intensive property, because even if you have a greater mass of something, you're going to also have a greater volume, and then the density can stay the same. So this is a formula that we have to know, and let's just practice some of these problems to work with that. Again, it's a really good idea to pause and work out problems yourself before you watch them being worked out, because the more that you participate, the more you'll learn. For this one, we are not given the mass directly. We are given the volume directly. We're looking for the density of 28.5 milliliters of liquid. So this is something that happens a lot in lab. You might have the mass of an empty container like a beaker. Then you put something in, you put some liquid in, and then you have the mass of the beaker with the liquid in it. If you want just the mass of the liquid, you need to subtract out the beaker. So the beaker and liquid minus the beaker gives the liquid. All right, so if I subtract the beaker from the beaker with liquid, I get 16.464 grams of liquid. Now I can put that as my mass, divide it by volume, and get the density. I have a whole bunch of digits. Let's take a quick look at our significant digits, which we are about to get to later in the chapter. When you subtract things, the significant digits are based on place value. So these both go 3 past the decimal, so we can use 3 past the decimal in our answer. That gives this 5 significant digits. Our volume has 3 significant digits. When we subtract, we base on the place value. When we divide, we base on the number of digits. So 5 significant digits divided by 3 significant digits should give us an answer that we need 3 significant digits. So here's the first, the second, the third. We take a look at the next one and we see that it's large. So we should report this as 0.578 grams per milliliter. If we were going to use this in further calculations, we might want to keep a couple extra digits, but just keep in mind that we only have 3 significant digits, and then round at the end. For this problem, this is the end, so we'll round to 0.578 grams per milliliter. Here we have another density problem. This time we are told the mass directly. We have a metal cylinder and the mass is 30.962 grams. And we are not directly told the volume. We took all these measurements of the cylinder, the height, the diameter, and we have this formula to calculate the volume. So the volume is the radius squared times pi times the height. And we're not even given the radius, we're given the diameter. And we know that the radius is exactly half the diameter. So since the radius is 1.20 centimeter over 2, it is 0.600 centimeters. I kept 3 digits because this is a division problem. I had 3 significant digits in my numerator, and I had an exact number in my denominator. This isn't 2 plus or minus 1. It's not even 2 plus or minus 0.1. It's exact. So it has an infinite number of significant digits. Between these two, 3 significant digits is a smaller number than infinity. So I can keep 3. Alright, so now I have the radius. So I can put these into the volume formula, 0.600 centimeters squared, either the pi button on the calculator or 3.1416, and the height 5.12 centimeters. Our radius and our height both have 3 significant digits. If we use this, we have 5 significant digits. The button on your calculator probably has even more. So we're going to take the smaller number and round our answer down to 3 significant digits. And the answer is 5.79 cubic centimeters, so centimeters cubed. We have centimeters times centimeters times centimeters. That is the volume. Since it has 3 significant digits, this 9 is really the last significant digit, but I'm going to keep a couple extra digits since I'm still using it in a calculation. There's a couple ways I can show this. I can use an underline like I did here. I can write the significant digits regular size and then have the next couple as a subscript. But however I do it, I have 5 significant digits in the numerator, 3 significant digits in the denominator, so my final answer is going to be rounded to 3 significant digits. So we have 5.34694 grams per centimeter cubed, and so we're going to round that down to 3 significant digits and report that as 5.35 grams per cubic centimeter. Here's another density problem where we are given the mass but not the volume. We have to calculate the volume. So this is a rectangular prism. The volume is going to be the length times the width times the height. The answer I come up with is 32.825232 cubic centimeters. That should have 3 significant digits. I'll keep a few more in the calculation and just underline it to show where it should be. So my calculator gives me a lot of digits, and then when I round down to 3 significant digits, I get 1.06 grams per cubic centimeter as the answer to report. There is another question: will the plastic sink or float in water? Water has a density of about 1 gram per cubic centimeter. This is more dense, and so this will sink in water. So this is another density problem, and we are given the mass directly, but not the volume yet. This time we did the volume by liquid displacement. We had some water in a graduated cylinder, read the volume, put an irregular shaped object in there, and read the volume again. The increase in volume is caused by this object, so the difference in the volumes that we read is equal to the volume of the object. So in order to cause that jump, the object must have had 17.6 milliliters as the volume. When we do the division, we get 4.150618 grams per milliliter. This should only have 3 significant digits because we have a 5 significant digit number at the top, a 3 significant digit number in the denominator. So we're going to want to take this down to 3 significant digits and report this as 4.15 grams per milliliter. So we're going to be doing a lot of conversions between things, and whenever you convert something, all you need is a relationship. Since density is the relationship between mass and volume, you can use it to convert between mass and volume. Okay, so this is our relationship. The density shows that for every 1 milliliter, that has a mass of 0.784 grams, and 0.784 grams would be equal to 1 milliliter. For every relationship, you can write 2 possible conversion factors. You can write the 1 mil on top, the 0.784 grams on the bottom, or you can flip it over. That's because since these 2 terms are equal, if we have x over x, that equals 1. So if you have 2 things that are equal over each other, then it equals 1. And if we multiply something by a conversion factor, we're multiplying it by 1 and we are not changing what it is. So we want to talk about this amount of acetone that we have, 43.8 milliliters, and instead of talking about it as milliliters, we want to talk about it as grams. But we don't want to change the amount that we have. So the way to change the units without changing the amount is by doing a conversion. So we take our amount that we're starting with, the 43.8 milliliters, and out of these 2 conversion factors, this one is going to be more helpful because the milliliters will cancel. So we have the milliliters canceling and we're left with grams, and it ends up being 34.3 grams of acetone. Let's do the same thing with this problem. Here's our relationship. For copper, 8.96 grams is equal to 1 milliliter. That one relationship can be written as two different conversion factors. And here we know the mass of the copper, and we want to talk about the volume, the milliliters. So we're converting grams to milliliters without changing the amount. We want to use one of the conversion factors to do that. The conversion factor that's more useful is the one with the grams on the bottom, so that it cancels. And when we do this, the grams do cancel. We divide 384.75 by 8.96 and come out with 42.9 milliliters, which is the volume. I think it's good to use the conversion factor method because we are going to be using it so much throughout the class, so it's good to get used to it. Some people do prefer to use formulas. So we have the formula for density, it's mass over volume. You can tell right here we have mass over volume, so if you ever forget, you can just look at a density and you'll know what the formula is. If we multiply both sides by volume, then we are left with volume canceling, we are left with volume times density equals mass. So here we go, volume times density equals mass, and that's exactly what we did here. We took the volume, we multiplied it by the density, and we got the mass. So if you had used this formula instead, you would have done the same thing and gotten the same answer. If we wanted the volume alone, what we would need to do is divide both sides of this by the density. And what we come out with here is that the volume is the mass over the density, or the mass divided by the density. And that's what we did here. We took the mass and we divided it by the density value, 8.96 grams per milliliter, and we came out with the volume. So if you had used this equation instead, you would have done the same thing and come out with the same answer.